Today we're going to finish up chapter 19 on electrochemistry. We're going to look at, again, Gibbs free energy, and we'll look at the relationship between Gibbs free energy and cell potential and the equilibrium constant. So this first slide, this is a neat slide because a lot of students, you've had a lab where you added different acids to different metals like magnesium, zinc, and copper. And so why does an acid cause a metal to dissolve? So if you look at this slide, it says the reduction of the hydrogen ion, that is the component of acid, or the hydronium ion, is easier than the reduction of a metal. So the hydrogen ion will be reduced to hydrogen gas, and you saw that when you added hydrochloric acid to zinc metal. You definitely saw this fizzing, and that was hydrogen gas. Maybe you collected that gas and did a test to prove that it is hydrogen. So if the hydrogen ion is going to be reduced, that means the metal will be oxidized, and so in this case they're showing zinc reacting with a hydrogen ion, forms zinc 2 positive, so it's oxidized and the hydrogen ion's reduced. Now you notice that when you tried this with copper, that did not happen. Hydrochloric acid could not reduce the copper, and the chloride ion in the hydrochloric acid is just a neutral ion. So then you had to add nitric acid. So when you added nitric acid to copper, you saw this brown gas given off. And what happens here is you have the nitrogen and the nitric acid reduced. So nitrogen and nitric acid, can you tell me what the oxidation number would be? Maybe hit pause, see if you can figure it out. All right, you should get positive 5 because oxygen is -2, and you got 3 of them, so that's -6. Hydrogen's a positive 1, so that means the nitrogen's a positive 5. So nitric acid will dissolve copper, and then if you try dissolving just like gold or platinum in nitric acid, it doesn't work very well. But if you add that with the hydrochloric acid, then you'll get a reaction. All right, so you really need to focus on this slide. Here's some equations you'll need to know for the next exam. So we've talked about delta G before, and we know how to calculate it directly, indirectly, in relation to delta H and delta S. And now we're adding a couple of new equations to that. So just to look at this again, you should know this equation here already. Delta standard Gibbs free energy change is equal to negative RT ln of K. That's our equilibrium. Okay. Well, standard Gibbs free energy is also equal to negative N, the number of moles of electrons, Faraday's constant, which is 96,485 coulombs per mole of electrons, and then the cell potential. And the same thing applies here. If you want this reaction to be spontaneous, delta G naught needs to be negative. All right. K over here has to be larger than 1, so that negative times the ln of K larger than 1 is a positive value, and temperature is a positive value. That would give you a negative delta G here as well. And then the other equation is we manipulate this equation to solve for the cell potential, the standard cell potential. And so by combining these two equations together, we get this equation. All right. So that's something to keep in mind. You're going to need to use all of these equations to solve for a problem. And what determines which equation you're using is what is the question asking for? Is it delta G, standard Gibbs free energy, or standard cell potential? And then are you given the equilibrium constant, or you're given the cell potential and you're asked to find delta G? So you need to work with these equations enough that you, when reading a problem, you can determine which one of these equations you need. All right, so this one says use the tabulated electrode potentials to calculate the standard Gibbs free energy change for the reaction. So what do you need to do here? And is the reaction spontaneous? So you look and you see that iodine is reduced. It goes from a 0 oxidation state to a -1 oxidation state. So what we have here is iodine gains 2 electrons and becomes 2 negative. So if that's being reduced, then the bromide ion has to be oxidized, and it does. It goes from a -1 state to a 0 state. Remember, pure elements in their standard states, have an oxidation number of 0. All right, so then at this point, you need to calculate the electrode potentials. So you have to look at a table, okay? So you look at the table, and let's see if I can pop that up here. So we're looking for the bromide and the. So the first thing I would look for is the reduction of iodine. So right there it is. I2 solid plus 2 electrons is 0.54 volts. All right, so we have that one. All right, and so if what we're looking for is the reduction of bromine. Okay. Well, it's not below. I don't see it below the iodide. Is that the case? Let's see. If that's the case, then we know that this reaction is not going to be spontaneous, right? That's what's so nice about once you get this chart down. Yeah. So bromine up here, it wants to be reduced. It has a greater tendency to want to be reduced than iodine. So here we're actually oxidizing. In our equation, we're oxidizing. So it's 1.09. So you write that down for the bromine, but remember, it's actually going in reverse, so it's a -1.09. So that's why we have to think about that. Okay, so we now have those two numbers that we get from the equation. So E anode, E cathode equals Ecell, and Ecell is equal to delta G. So there's our plane of action to solve for the problem. So we're going to calculate the Ecell for this reaction based on what we saw on the table. Plug that into this equation, and we will find delta G. All right, so we looked that up and we said, okay, the anode is where the bromine is being oxidized, and the cathode is where the iodine is being reduced. And remember, here's the equation you need to know. And the thing you need to remember about this equation, it takes care of the sign change, right? So you get these from the table for reduction. Both of these is a reduction. Now this one's not quite right, but when we're going to say that's the anode, that's really oxidation. So it's E standard cell potential of the cathode minus the anode, so it's 0.54 minus 1.09, and that's where we get the negative 0.55 volts. All right. So standard cell potential is E cathode minus E anode. You look at the reduction potentials, plug those into this equation, and because we're subtracting the anode, that makes that a negative 1.9. So you can do it that way, or you can say, well, this is really an oxidation, so I know that's negative. And if I take that and then I add that to this, I get the same answer. So either way you want to do it, it's really easier just to take them off the table and plug it in the equation and get it. So because it's negative 0.55, we know that this reaction is not spontaneous. It's remember, we have to have a positive cell potential for it to be spontaneous. So knowing that this is negative, we know delta G, standard Gibbs free energy for this, should be a positive value. And if it's not, we've made a mistake. All right, so we plug it in. We have N times Faraday's constant times the cell potential. And you go, what's N? Well, notice on both of these half reactions, it's 2 electrons. So if this had been a 2 and this had been a 3, then you put in 6 because they have to have the same number of electrons lost, number of electrons gained. So in this case, they made it nice for you. They made them both 2. So we have negative 2 moles of electrons. And that's probably the most common mistake I see is students forget there's a negative sign here. All right, and so negative 2 moles of electrons times Faraday's constant times the cell potential, which is a volt is joules per coulomb, and so that's why you want to do this so that the coulombs will cancel out, the moles will cancel out, and you'll be left with joules, which is the energy unit for, well, kilojoules is the best energy unit for delta G. In fact, if I wrote this, it would probably be at the end 1.1 kilojoules, but they have 1.1 times 10 to the third joules is their answer, and that's fine. Either one of those answers. Notice it is positive. That makes sense because the cell potential was negative. So if you know this is negative, the cell potential, and you don't get a positive value for delta G, it's probably because you've missed the sign there. You missed the sign on that equation. So again, not difficult. You look at the equation, break it down into its half reactions, look up the cell potentials for each one of those reactions, the anode and cathode. It's always cathode minus the anode. That's how you find the standard cell potential for the reaction. All right, and then because they're asking you for delta G based on cell potential, that's how you know it's that equation. And another thing I guess it's important here, it is not spontaneous under standard conditions. Since we're solving for delta G naught, remember that's standard conditions. All right, you got another practice one there. All right, so let's look at this one. Refer to the tabulated electrode potentials to calculate K for the oxidation of the hydrogen ion. All right, so what we know is, if I know what delta G naught is, delta G naught is equal to negative RT ln of K. So if I can solve for that, then I can solve for K. And because they say look at the electrode potentials, we know that delta G naught is equal to negative N times Faraday's constant times the standard cell potential. So there's our plan of action. And then what we see is the copper is being oxidized and the hydrogen ion is being reduced. All right. So we need the reduction value for the hydrogen ion, and we need the standard reduction for the copper, even though it's being oxidized. All right, so let's look these up real quick. So let's see. Copper, shouldn't it be down? There's the copper. All right, copper 2 positive, middle of the screen. No, that's not what we want. The one above that. Copper 2 positive plus 2 electrons forms copper solid, 0.34 volts. 0.34 volts. And then the hydrogen, the reduction of the hydrogen. Let's see. You guys have probably seen it before I do. All right, there it is. All right, so 2 hydrogen ions plus 2 electrons forms, and that's 0. I don't, yeah, we should know that one. Shoot, I don't know why I was thinking about that. That's just the standard reduction potential, right? All right, so here we go. And they do it in this equation. You can do it this way too. I forgot about that one, actually. I usually use those 2 above, and I think that's what I do. Is I know that those 2 equations will always work, but here they've actually combined those 2 equations into this final equation, and that's fine. You can do it that way too. Makes it a little faster. Okay, so it's still the same process though. You are going to find the standard cell potential, and so the copper is being oxidized and the hydrogen's being reduced, and it's 0. So cathode minus anode gives us a negative 0.34 volts, and you go, it's not going to be spontaneous. And then here's where it gets a little easier. You put in the standard cell potential, and again, the number of moles of electrons being exchanged in this reaction is 2. Divide by 0.0592 volts. The volts cancel out, and we get a log of K of a negative 11.48. Well, you know then K is going to be a small number, because that's going to be, to get rid of the log, you have to do 10 to the, do the inverse, which 10 to the x of both sides of the exponent. So 10 raised to the negative 11.48 is 3.3 times 10 to the negative 12th. That's a really small K, so you know the reaction mainly stays on the reactant side. The reactants are not converted to product. All right. Let's go back. I just want to, again, say how you could have done this. You could have solved for delta G here, and then plugged it into this equation up top, and then solved for K. You would have still come up with the same answer. All right, I'll give you another example there. All right, so here we're changing the game a little bit. We're not talking about 1 molar concentrations of the electrolytes. So we're not under standard conditions anymore. That's what you need to remember here. We're not under standard conditions. All right, so there is a relationship between the reaction quotient Q, the equilibrium constant K, and standard Gibbs free energy. So changing the concentrations of the reactants and products so that they're not 1 molar will affect the standard Gibbs free energy. Because delta G determines cell potential, the voltage of the cell will be different when the ion concentrations are not 1. So that's what they're showing in this diagram, is that when it's 1 molar concentrations of the electrolytes, the voltage is 1.10, but if we change the concentrations, the voltage changes, non-standard conditions. So we need a new equation. We need a new equation, and it's going to look a lot like, let's write this equation down. So just to kind of give us a reference point, and that's why I'm saying The last chapter was important. So we know under non-standard conditions, delta G equals delta G naught plus the RT ln of Q. All right. So now let's translate that into cell potential. So here we have it. We have the equation that we learned in the previous chapter. We substitute in for this part. And delta G non-standard conditions is the same equation, just notice it's not standard here. And then the relationship between delta G and delta G standard is we've got this correction factor of RT ln of Q. All right, so then what we can do here is we want to solve for this, right? So we divide both sides of the equation by negative N over F, the number of moles and the Faraday's constant. Well, that cancels out this one. And then we got RT over N over F, and it changes the sign to a negative here. So we've divided the whole equation by negative N over F, or negative NF, and we get the cell potential under non-standard conditions. Now, this equation is called the Nernst equation. You need to memorize that. It's kind of like the Henderson-Hasselbalch. I mean, as far as it's one of those equations you really need to know. But it is really based on, generally I don't memorize. I usually just know this, and then I plug in the NFE and FE and solve for it here. So if you can do that, you can go from here directly to there, or just memorize the Nernst equation. It doesn't matter. Well, R is a constant. If the temperature is held constant, and the Faraday is a constant, if you say all of those are constants, then we get 0.0592 volts over N. All right. So I've memorized this equation. This equation's actually, just combining RT and F. I guess it makes it a little faster if you know that one. Makes it a little faster to get through the problem. All right, determine the cell potential, not standard cell potential, cell potential. And that's the key right there. Cell potential for the electrochemical cell based on the following two half reactions. All right, so we have an oxidation of the copper, and we have a reduction of the permanganate ion, or the manganese if you want to look at it that way. So the first thing we need to do is find out I think you find out the voltage, but they actually write the concentrations down as well. But to me, you got to find those voltages. So once you find the standard cell potential from the voltages of reduction voltages or reduction potentials, then we're in business, and we can use this simplified equation down here at the bottom. So you look on the table, it's 0.34 volts for the reduction of copper. It's 1.68 volts for the reduction of permanganate. The reduction occurs at the cathode, so the standard cell potential is the standard cathode potential minus the standard anode potential, so it's going to be 1.68 minus 0.34, and we get for an answer 1.34 volts. All right, so first thing we know here is we got a positive cell potential, and so we're hoping that based on this positive cell potential that the standard cell potential, we're hoping that we get a positive cell potential. Now, it depends on that RTNF ln of Q, and so we're going to see what the effect of that is. So it does depend on the concentrations of the electrolytes. I don't think it's going to change it that much. All right, so here we have it. The cell potential, not standard cell potential. Just make sure you get, I mean, a lot of people forget that these are different things. So cell potential, non-standard conditions, is equal to the standard cell potential minus 0.0592 divided by the number of electrons exchanged, which is 2. Well, here, no, let's look at that. Here's what we do. We got 2 here. We got 3 here. Both numbers go into 6. There we go. We finally get one where they're not the same. All right. So n is equal to 6. All right. And then we know that if this is our final reaction, that Q is products over reactants. Well, notice this is the only one that's aqueous. So again, throw back all the way to chapter 15. Pure solids, pure liquids do not go into the equilibrium expression. Over here, the copper doesn't go in because it's a pure solid, but these two go in because they're aqueous. So that's why this looks like that. It's always products over reactants raised to the correct exponents. So yes, you do have to multiply this entire equation by 3 and this entire equation by 2 to get a balanced chemical equation. And so that's important because that's what's going to give us our exponents that we have here. Plug in the concentrations given, raise to the appropriate powers, and then solve. And so we have the standard cell potential minus our correction factor here due to the differences in concentration, non-standard concentrations different than 1 molar. And we get 1.34 volts minus a negative 0.065 volts. And minus a negative makes it a positive, and so our new cell potential is 1.41 volts. All right. 1.41 volts. We actually increase the voltage of the cell. That's a pretty, it's a lot of steps. It's, it's, the main thing is the Nernst equation. You know the Nernst equation. I think that's about as hard as they get in class. Other than that, I just wanted to say, I want to stress this check here because that's what I was thinking about too. So the answer has the correct units, voltage, and the value of the cell potential is larger than the standard cell potential as expected based on Le Chatelier's principle, because one of the aqueous reactants has a concentration greater than standard conditions, which forces the reaction to the right. And because it's forced to the right, that's going to have a greater tendency towards the products, and the more we go to the products, the more voltage that's going to be generated. So good. I like this check. I think it's worth talking about that. If you go back and you see that the reactants were in higher concentration than standard conditions, and this product is much lower than standard conditions, this reaction is going to shift to the right, which generates more voltage. All right, so here is a strange type of cell. So every cell we've been doing so far has been, you looked on the table, you found out what was being reduced, what was being oxidized. But you can actually have a difference in voltage based on just differences in concentration. So you use the same substance in both cells, both half reactions, but they're of different concentrations. And so the difference in energy is due to the entropic difference in solutions. The more concentrated the solution, the lower the entropy. Makes sense because the more solute particles you have occupying a certain volume, the less spaces those solute molecules can occupy, so its entropy is lower than a less concentrated solution where you have less solute and more in the same volume, so the solute can occupy more spaces in a given amount of volume. So electrons will flow from the electrode in the less concentrated solution to the more concentrated solution. All right, so electrons will flow from the electrode in the less concentrated solution to the electrode in the more concentrated solution. So oxidation occurs at where the less concentrated solution, the electrons leave, they go over to the concentrated solution, and that's where the reduction occurs. So this is what we're talking about. We have an electrode of copper and an electrode of copper, and then the solutions are both 1 molar in the copper ion. And notice that's standard conditions. These are exactly the same. So there's no difference in potential energy. In this next, the one on the right here, we've increased the copper 2 positive ion concentration to 2 molar, and that's why it's blue, because it's got more. Copper 2 positive ion is blue in color, and the more concentrated it is, the more blue the solution becomes. And so in this case, because this is less concentrated in here, the electrons will leave. They'll go over here, and they'll come out here, and then they'll try to reduce this copper 2 positive ion solution to 1.010 molar. That's what we try to do, is get back to the standard condition. All right, so this is called a concentration cell. Same substance, same electrodes. We're just looking at differences in concentration. This is kind of the way, have you ever seen those clocks that run on a potato or a lemon or something like that? That's what they work on. The electrodes are a little different coating. You stick those in there, it makes a difference in concentration, and therefore you can generate a voltage difference. It doesn't have to be much in order to power the clock. All right, so I'm not asking you to do a calculation here. I'm just asking you to see that when you have the same electrodes and the same electrolytes, that yes, you can have differences in potential energy. So you'll have a cell potential based off of non-standard conditions of the constant. So over here it's standard, right? 1 molar concentrations of everything on the left. Now we're in non-standard conditions, and that creates a cell potential. All right, the rest of chapter 19, I'll kind of breeze through it. You can read it. Some of you maybe should have read this at the beginning. It's really just showing you applications of electrochemistry, like why you need to know it. And it is going to focus on batteries, but it can also focus on the generation of hydrogen gas, so an electrolytic cell. And it's important if you are interested in saying, why aren't we running cars on hydrogen instead of gasoline to reduce fossil fuel emissions or greenhouse gases, then this is the kind of stuff the rest of the chapter is going to focus on. And then what's the difference between a dry cell that you would use in a flashlight to your lithium ion battery. So that's what the rest of this chapter is about, is applications of what you've just learned. So you've gone through the type of problems, the mathematical problems used to calculate standard Gibbs free energy, standard cell potential, the relationship between number of electrons, Faraday's constant, and the cell potential and the Gibbs free energy. We've also looked at the relationship between Gibbs free energy, cell potential, and equilibrium constant. And we've talked about the theory behind that. And then ultimately we end up with the Nernst equation for non-standard conditions, which is really important. So make sure you know that. But again, the rest of the chapter, it's this type of thing, batteries, an acid dry cell. So you know that when you look at a copper, like a Duracell battery, you have this raised area, and then you have this recessed area on the other end. The raised area is the positive terminal. It's a rod that's in the middle of the battery, and then so that's one electrode, and then the casing here is another electrode. That's your negative. You know, that's where your cathode is. All right. So at the anode, what happens at the anode? It's always oxidation. So the zinc is being oxidized, and what's happening at the cathode is the cathode's the graphite rod, and what's happening is this solution is being reduced. Okay. So just look at that, and so they talk about what the electrolyte paste is, and the cell potential for this is 1.5 volts. Okay. So what you kind of see here, if you look at this closely, you see this, here's your salt bridge, so to speak, the blue that separates this solution and the rod from the outside here. So it is, all the things are there. You have two half reactions. They're not together, and you have you have what we would call a bridge between the two. So that's what this blue is here. Now, let's see if they do a. So this is like a non-alkaline battery. This is actually just your regular battery. Okay. So then we go to a Duracell battery, which is an alkaline battery. It's a little different, but you can still see you have the positive terminal. The zinc or magnesium is being oxidized, and then at the then you have your solution, and the magnesium 4 oxide is being reduced. Longer shelf life than acidic dry batteries, regular than just your regular battery. Little corrosion of the zinc. So they did, let's see, did they go back and say about that separator here? Yeah, they don't really, they just say the case. They don't really tell you about the separator. That's what I'm saying. You got to have a separator, just like you got to have a salt bridge, right? You got to have a salt bridge. Then you have your lead storage battery. This is your car battery. And so the anode's lead, and the cathode is lead coated with lead 4 oxide. So the lead 4 oxide is reduced. And so each individual cell produces 2.09 volts. So then you have 6 cells in there, and that gives you a 12-volt battery. So you know what happens here is, well, it's a little more than 12 volts, not much. But so what happens is, you know, if your battery's not acting right, you can hook up an instrument to it, and it'll say maybe you're only getting 10 volts. And then the guy will say, you've got a cell out of your battery. That's generally what happens. It's one of the cells goes out, and you need a new battery. So you might get away with a 10-volt start if it's not too bad. It's hard on the car, and so that's generally what happens, and you need a new battery. So the advantage of the lead storage batteries is that it is reversible. This reaction is reversible, and we can recharge the battery. It's rechargeable. Downside, it is heavy. All right, then we get into NiCad batteries. You probably have used some of these. These are called metal hydride batteries. So what you have here is you have cadmium being oxidized, and cadmium being oxidized produces 0.81 volts. And you have this nickel, usually it's a nickel oxide with a hydroxy attached to it. The nickel is being reduced, and so it generates 1.3 volts. Again, rechargeable, long life, but if it's recharged incorrectly, it can break it down. Now, this is what everybody's interested in, is the lithium ion battery. So lithium, you have an anode. Anode is graphite. It's impregnated with lithium ions. Cathode is a lithium ion transition metal oxide, so lithium oxide if you want to think of it that way. And the lithium ion migration from the anode to the cathode causes a corresponding migration of charge. So what happens is the positive ion migrates one way, that causes electrons to migrate the other way. And so we use those electrons to power your cell phone. They are rechargeable, they have long life, they're very light, they're nothing like those lead oxide batteries, and they have a great charge energy density. But here's what I would like them to show on this. Between the graphite and the lithium oxide, there is a separator so the reaction doesn't just happen freely. We want to get the work out of the electrons. Well, that separator, I wish they would have shown it, because it's kind of like, that's what I was trying to get at back here, is there is this absorbent or separator here on the Duracell battery. We have to have the same thing on the lithium battery. So I don't know if you remember a few years ago, people's cell phones, they were sitting on them and it would cause the separator to break, which would allow the lithium ion and the electrons to exchange automatically. Generates a lot of heat because they are a great energy density and they would catch fire. So that's why you generally can't check a lithium ion battery on a plane, because maybe you've damaged the separator, you don't know about it, and it starts heating up because this reaction then becomes spontaneous and it flows very quickly and generates a lot of heat and actually catches fire. So that's the concern here. So they have high energy density. I mean, just think about it. It powers your cell phone for the whole day. Fuel cells, this is where we're trying to get to. This is ultimately what we're looking at when we talk about maybe a car running on this at some point, where you fill your tank full of hydrogen and the hydrogen then reacts with oxygen and we generate water. So so we're not generating any greenhouse gases, although water is a greenhouse gas, but it's not like CO2. And so ultimately this is what we'd like to have as a car. You just put in some hydrogen, out of the tailpipe comes water. Downsides, the fuel cell is really expensive, costs more than the car. And so you have to make a really cheap car, and then you're really just buying a fuel cell. It's coming down in price. There are fuel cell cars out there. They're usually used as fleet vehicles. They're not sold to the public for the most part, but this is where we'd like to go. What's cool about it right here, they never run down. This reaction keeps happening till you use up all the hydrogen. And so as long as you keep supplying hydrogen, the reaction keeps going and going and going. So overall, you may just want to look at these slides to say, again, galvanic cell or a voltaic cell, spontaneous reaction. The cathode draws the electrons and has a positive charge. The anode releases the electrons, has a negative charge. And then the other type of cell, which we really haven't focused on, is the electrolytic cell. And that is where the electrons are drawn off the anode and the electrons are forced towards the anode, so that we're recharging it. We're doing the reverse reaction. All right, so here's what that looks like. So here we have a zinc electrode with a zinc electrolyte. And we already know, we've done this reaction over and over. This is a spontaneous reaction. Zinc will, because it has a greater, let's see, is it a greater? It's a greater reduction potential than the copper. The copper has a greater reduction potential than the zinc. The zinc oxidizes, the copper 2 positive ion reduces, and we release electrons, and this generates a voltage of 1.10 volts, positive value. So this is a spontaneous reaction. This is a voltaic cell. But what if I replace the voltmeter here with an energy source that reverses the flow of the electrons? Well, that's possible. And when we do that, we now have gone from a voltaic cell to an electrolytic cell. We are forcing the reaction in reverse, so we're recharging this battery. And so now what I want you to remember, this is the most important part of this. When you make it an electrolytic cell, the anode becomes the cathode, and the cathode becomes the anode. All right? So look at the reactions. Copper solid now is being oxidized, and zinc 2 positive is now being reduced. So remember, reduction always occurs at the cathode. Oxidation always occurs at the anode. When we do an electrolytic cell, the reaction's reverse, so the cathode now is where the zinc is being reduced and the copper is being oxidized at the anode. So just keep that in mind. That's really important that you know that. That's how we know that you know the difference between a voltaic cell and an electrolytic cell. Another example of electrolysis, you've already probably know about this, but you can pass electrical current through water, generate hydrogen gas and oxygen gas. This is what a lot of people think, like this is how we would generate hydrogen gas for hydrogen-powered cars. The question is, where do you get the energy source to generate the hydrogen gas? If you're burning fossil fuels to generate electricity, to generate hydrogen gas, not really good for the environment. If you can replace a fossil fuel electricity generator with something like solar energy, that's good. Maybe thermal energy from the ground or something like that, that's good. But that you're like saying, well, how much hydrogen gas can I generate that way? Well, that's the question. That's how much hydrogen gas, because that's takes quite a bit of energy to separate hydrogen into hydrogen and oxygen. And we're having to generate enough hydrogen gas to power all the cars in the United States or the world. I guess to be a lot of hydrogen gas. And so the question is, what's the energy source? And if it's fossil fuels, it's not really helping us. All right, these are just a couple of things to look at. Over voltage, just mean, I'm not interested in over, I mean, we could talk about, I'm not going to test you on over voltage, it's not that important. Yeah, I'm not really interested in the rest of this chapter. It's not my, this is beyond what is expected. And you may want to read this about electroplating. A lot of people are interested in that. How do you electroplate something? I'm not testing you on that. So the rest of this chapter, I'm not interested in. So as far as what you're responsible for, we're not doing stoichiometry of electrolysis. So as far as what you're responsible for, it really stops at concentration cell. All right. So that's the end of chapter 19. If you have questions, email me. I'll be glad to develop more videos, or if you've got a specific problem you want to see worked out, just tell me what's the problem number, and I'll work it out for you. So that's the end of 19.